I'm Tomasz Zawadzki, and together with Luse, we'd like to show how NVMe device emulation in SPDK works and why it is the answer for some of the applications. This session will start with challenges met in certain use cases and then explore the main pain points for one of them, followed by components used to emulate NVMe device and two chief applications for the idea. First of all, this is not an answer to all the problems. There are specific usage models which historically have worked in suboptimal way or are not possible at all. Let's start with SPDK setup. After configuring the SPDK in preferred way, layering BDEVs on top of each other with preferred BDEV services, at some point comes the time to consume them. Over network, that would be iSCSI or NVMe target, vHost target for the VMs, or changing application to use the BDEV APIs directly. Networking is very well standardized and will not be the main topic of this presentation. Instead, let's focus on the following. First, exposing the storage to VMs. SPDK interacts with virtualized environments using vHost and virtio, which come with their own set of limitations and requirements that will be explored in depth over a couple next slides. Another is using application without rewriting it to the BDEV API, a very common request for SPDK that was hard to do in an efficient way. And then last but not least is the secret sauce, the non-standardized or software and hardware specific interfaces. This one will be shown by Paul later in the session. All of them require some type of interfacing. But why reinvent the wheel? In storage world, that common standard is NVMe. So far, it was either very hard to do so or not possible to use in the presented cases. NVMe driver is the cornerstone of SPDK, and its efficient usage through the BDEV layer is the main design goal. We would like to present how to take advantage of it even further. Please bear with me for a little while. Before getting back to NVMe emulation, let's take a step back and explore exact pre-requirements and inefficiencies of the virtualized use case. SPDK uses virtio and vHost to expose storage to the VMs. Virtio is a set of paravirtualized driver specification with specific set of protocols in mind. Shown here are virtio-blk, virtio-scsi, virtio-net, while there are many others. Virtio is responsible for specifying common layout and set of mechanisms for device discovery and communication via virtqueues. Meanwhile, vHost allows to communicate to the VM parameters of the virtual devices. The devices can be configured even from user space processes, as is the case with SPDK vHost target. Finally, when the devices are created and connected to the VM, I/O is done through the virtqueues, which are directly accessible from the VM process and the vHost target process. The main drawbacks of this solution is that there are requirements for the guest VM to contain drivers for specific virtual device. Another is that the messages in the virtqueues contain specific commands particular to the virtual device, such as blk or SCSI commands, along with their own set of limitations and translations required when considering BDEV API or NVMe in general. As established, there are two virtual protocols broadly accessible and used today. virtio-blk, that contains simple set of commands, and single controller containing single device, as well as virtio-scsi, which handles more capable SCSI protocol and allows multiple devices per each controller. What about the two pain points from previous slide, using standard NVMe driver in guest VM and handling the traffic directly with NVMe commands? Next logical step would be probably virtio-PCI, which would enable sharing a generic PCI device or an NVMe-specific virtual device. Unfortunately, virtio-PCI was never officially standardized, and there are actively no use implementations. Meanwhile, virtio-NVMe has been standardized and implemented in SPDK, but human support was never merged, currently maintained as out-of-tree patches with minimal adoption. Those and similar challenges are met in other previously mentioned use cases. So, since specific issues were described, let's go back to the solution with NVMe, with emulation of NVMe devices. Not that obvious at the first glance is that SPDK had logic for NVMe emulation for some time already. The key to that is careful examination of abstractions involved in NVMe target, where any BDEF can be exposed as NVMe namespace, which are later attached to a specific NVMe controller, which contains all the logic one would expect from the NVMe controller, regardless if it is a local or a remote one. It handles NVMe commands and responds with the expected completions. Then that particular controller is exposed via NVMe transport, which handles all the connection management and encapsulation of the NVMe commands. Initiator is similar in that the NVMe transport unpacks the NVMe commands for further processing. The missing piece of the puzzle to actually utilizing the described NVMe emulation lays in the NVMe transport itself. During the target and initiator communication, compatibility is assured by using a common transport on both ends. Networking for long has had specifications for common protocols between two endpoints. This is exactly why those have been used in NVMe specification as the transports. As such, they were always related to particular fabric, such as RDMA, TCP, or fiber channel. Since NVMe transport in SPDK is exactly what the name says, a generic way to submit NVMe commands, this does not have to be over fabric, nor the initiator has to be on the other side of the network. With the requirement gone, it opens up possibilities to use NVMe emulated devices in many more ways. There are a set of changes needed for NVMe transport in order to allow for that happen. And then going even further, thanks to the work done by Seth Howell, the custom transport can be plugged in and maintained even out of SPDK 3. One of the two discussed new usages will be the one facilitated with mediated devices. This one alleviates the drawbacks described in the vehicles and virtual section. First, a short introduction to the mediated drivers mechanism, historically used for sharing, for example, sharing single device such as, let's say, GPU to multiple VMs. A specific driver is written to interact with mediated core, let's call it backend driver. Meanwhile, the mediated core provides an interface to device management to be used by different devices. One example of the front-end driver consuming the NDEF is VFIO, which on its own provides unified API for direct device access. This allows directly passing through one of many virtual functions to the VM. That virtual function then is seen on the guest VM as yet another PCI device without the need for specialized virtual driver. But the most interesting twist on this was accomplished by colleagues at Nutanix with libmuser. The backend driver does not have to be backed by physical device. libmuser is open source project on GitHub that provides Emulation kernel module and user space APIs to create a device using that particular kernel module. Please note how similar this scenario is to the vhost case, with chief difference being that the NVMe switch to the NVMe target. All the pieces should fall in the expected places. New custom NVMe transport added in form of a plugin for libmuser, where libmuser interacts with the user kernel module backend driver to configure the device. Then VFIO frontend driver consumes that device using VFIO. At this point, even other applications could consume the device via kernel if bound to the NVMe driver. In this particular example, the virtual function is passed directly to the guest VM as a PCI device. After the device is configured and attached in the VM, NVMe transport can directly interact with the device registers and queues. Key points on how this resolves the aforementioned challenges from the vhost and virtual case is that there are no requirements on the guest VM for specific driver, and the directly accessible device queues contain actual NVMe commands. libmuser is a project available on GitHub. Meanwhile, the custom transport in NVMe is available on SPDK Gerrit review board. So then again, as it is often the case in software development, this can be improved even further. There is an improved solution in the works right now. So as long as the main benefits of no specific driver and direct access for NVMe submission and completion are kept, the way to configure the devices can change. In development right now is the VFIO over socket solution, which would skip the mediated driver devices altogether. Instead, configure device directly in the guest VM using unique socket. This approach requires acceptance of upcoming changes by the QEMU community, and it is an area of active development. If you are interested, please join us at SPDK Slack on the VNVMe channel. So this concludes the introduction to the emulating NVMe devices using SPDK NVMe target, and first of the two sample use cases. For the next one, please let me pass it to Paul. Please take it away.
Hey, thanks, Tomek. Can everybody hear me?
Yes.
Oh, excellent. Okay. Okay. So yeah, awesome. So you just heard about how the NVMe device emulation code in SPDK was originally developed out of necessity, right, to implement an NVMe over Fabrics target that can have pretty much anything backing it, right? That's a key point out of that. It doesn't have to be NVMe backing it. It's BDEVs, right? So your BDEV can be anything really. So I mean, if that's not cool enough, then you just saw how the device emulation code has a really cool home in this upcoming VFI over sockets with libmuser in drastically increasing performance of storage served up to virtual machines with SPDK. So this next use case is SmartNIC. This section is, of course, not about SmartNICs, so it's my pleasure to tell you you only have 4 slides left and you can get rid of your headsets. My ears, I know, are aching from wearing this thing all morning. But really, this is just to highlight how the NVMe device emulation code has found yet another home that it wasn't intended for within SmartNICs. Next slide, please, Tomek. Okay, so what is a SmartNIC? Give us one click. So a SmartNIC is really a NIC that can offload something from the host CPU. And here's some lists of things: encryption, decryption, firewall, TCP/IP, web services, pretty much anything you can think of. when we were preparing for some of this, somebody had asked me what makes a SmartNIC smart, and it reminds me. I know we've got lots of people with lots of vast storage experience attending this forum. Some of you may remember something called an intelligent RAID HBA, right? Back when direct attached storage was the cool kid on the block, and intelligent RAID HBAs had exactly this same kind of capability on them. They had an offload engine on them that did exactly this kind of stuff. They typically didn't do TCP/IP, but it was really around offloading interrupts and offloading RAID calculations and providing additional memory bandwidth, those kinds of things. So this is really the same kind of thing, right? Smart is it's a marketing term, just as with intelligent HBA was a marketing term. So think of it as anything that can offload the host CPU so that you can use those valuable cycles for something more productive and move some of the compute closer to where the storage and network is at. Okay, click. Now, the SmartNICs can come in all sorts of shapes and sizes. They can be ASIC-based, FPGA-based, or built with an SoC, right? The I/O processors I mentioned were pretty much system on a chip, an SoC. And if we click one more, depending on how it's implemented in hardware, these things can vary like dramatically. Price performance points are all over the map. I tried to find a really cool graph showing some of these things, but some of the stuff, the information's fairly difficult to find. But just keep that in mind. You're not going to go out and find a $100 SmartNIC anywhere that that you're going to be able to just plug in and use. Okay, next slide. And one click. And the Doreo group has a couple of really cool little snippets here I just wanted to share to at least say something about SmartNICs in the industry before I talk about where SPDK device, NVMe device emulation can fit into the picture. So this first one is pretty interesting, right? I didn't realize that there were so many vendors, but no fewer than 10 have launched SmartNICs, and the SmartNIC market is expected to grow to 600 million in the next couple of years and represent, roughly a quarter of the entire Ethernet adapter market. So this is kind of a big deal. And when you zoom in on the data a little bit and find out where these things are being used, you'll see it in the top 4 U.S. cloud service providers. Amazon in particular, because they're fairly public about their use of this. Just the top 4 cloud providers account for 90% of the SmartNIC market to date. So these things are finding homes in cloud storage all over the place, and we just continue to expect to see that grow over time. Okay, next slide. Okay, so this I borrowed with pride from Sasha and Oren from Mellanox. They gave a great talk 2 years ago at the same summit when we were actually able to have it in person. And I encourage you, if you want to find a little bit more detail about SmartNICs, their presentation has information with performance data in it and more details on use cases, all sorts of great stuff. But these were great pictures, so I thought I'd steal them from them. So this is really just a high-level common use case picture, and then the next one I have to show you, we'll go into a little bit more detail. But looking at the picture in the middle, you can see the host is in that greenish type area. The SmartNIC itself is an HBA that is plugged into the host. And if we look at the application/file system type box, that's going to communicate down through the kernel driver through the regular storage stack path. And then you can see where we've got the emulated NVMe device is coming off of the SmartNIC itself. So the SmartNIC is pretending like it's an NVMe device, and all of the logic that implements the NVMe device is our NVMe device emulation layer in SPDK. So why is that important? Why is that interesting to do? Well, again, it's about moving these cycles away from the host CPU onto the SmartNIC, where they can do a couple things. One, be closer to where the storage is, and number two, enable something like what's shown in this picture here, where with the SPDK NVMe initiator at the bottom of the stack, you can go right back over the wire, and you basically got a disaggregated storage solution with the SmartNIC managing the storage. Okay, next slide. Okay, and then finally, again, from the 19th Summit, just a little bit more detail. You can see within SPDK, our NVMe device emulation layer is the full controller. It's emulating I/O queues, admin queues, registers, right? The host really just thinks it's talking to a local NVMe device. And then again, to highlight the fact that the NVMe device emulation layer, it completely abstracts everything behind it. On your SmartNIC, you now have the ability to run a custom VBDev. You can add whatever virtual BDev you want. You can add one of the SPDK VBDevs, compression, crypto, logical volumes, any of the VBDevs will work. And then you've got your BDev, which can be local storage or can be NVMe and going out over NVMe initiator to targets offsite somewhere. Now, the other thing that I wanted to point out here at the bottom, you see we've got NVMe over Fabrics with the RDMA plugin, the TCP/IP plugin. You could also do something custom here. And a good example is what we just saw with the Mediated devices. But in a SmartNIC environment, you could probably come up with all sorts of other interesting things you can do to go off box with your storage. Okay, so that's what we've got for how NVMe device emulation found its home into SmartNICs. Vladimir, I'll turn it back over to you to wrap up.